Welcome back. I hope you must have gone through our earlier video on which we had a quick recap of probability theory that is important for our further discussion regarding Bayesian learning. In this class, we are going to relate Bayes' theorem that we discussed in the last class with the machine learning theory. So, how Bayes' theorem can be useful for solving machine learning problems that we are going to discuss next. In machine learning, for solving a particular problem, we have a hypothesis space. So what we mean by hypothesis space? The hypothesis space includes all possible hypotheses, those we may use to solve the problem. But even though we are having many hypotheses in the hypothesis space, those can be used. We are interested in a hypothesis that is best suitable or optimal to solve the problem. Thus, in machine learning, we are often interested in determining the best hypothesis from some space H, given that we have some training data D. That means we always demand the most probable hypothesis H given the training data D, and in addition we may have some initial knowledge about the prior probabilities of the various hypotheses in the hypothesis space capital H. Bayes' theorem provides a direct method for calculating the probability of a hypothesis based on its prior probability. The probabilities of observing various data given the hypothesis and the observed data itself. So Bayes' theorem needs three different quantities: the probability of a hypothesis based on its prior probability, the probabilities of observing various data given the hypothesis, and the observed data itself. So Bayes' theorem allows us to calculate probability of hypothesis H given training data D. So let us try to write the Bayes' theorem now in terms of hypothesis and the training data set D. So we can write the expression as probability of H given D is equal to probability of D given H multiplied by probability of H divided by probability of D, where probability of D given H is the probability of observing data D given some hypothesis H that holds. That means if the hypothesis is true, what is the likelihood of that data being generated? Or in other words, we may say that if the hypothesis H is true, what is the probability of D being generated? Probability of H is the prior probability, or it is the initial probability that hypothesis H holds before observing the training data. So it gives the probability of the hypothesis prior to observing the training data. What is probability of D? This is the prior probability of training data D. That means the probability of D given no knowledge about which hypothesis holds. And based on these three quantities now, we are interested in computing probability of H given D, or probability that H holds given the training data set D. Probability of H given D is also called as posterior probability of H because it reflects our confidence that H holds after we have seen the training data D. Thus, Bayes' theorem provides us the posterior probability of H, that is, probability of H given D. Using Bayes' theorem, we defined probability of H given D is equal to probability of D given H into probability of H divided by probability of D. In many learning scenarios, the learner considers some set of candidate hypothesis H and is interested in finding the most probable hypothesis H that belongs to capital H, that is the hypothesis space, given the observed data D. Any such maximally probable hypothesis is called as a maximum a posteriori hypothesis. Maximum a posteriori hypothesis, or in short, MAP hypothesis. We can determine the MAP hypothesis by using the Bayes' theorem to calculate the posterior probability of each candidate hypothesis. So more precisely, if we try to find out H map, that is the maximum a posteriori hypothesis, we can formally write down the mathematical expressions as follows. H map is equal to ARG max of probability of H given D for all hypothesis H in the hypothesis space capital H. So what we mean by this? We are going to compute the posterior probability of hypothesis H given the fixed data set D. We are computing this posterior probability for all the hypotheses in the hypothesis space, and will be picking up the hypothesis from the hypothesis space H such that its posterior probability for given data D is maximum. So by replacing probability of H given D by making use of Bayes' theorem, we can write H map is equal to ARG max for all hypothesis H in hypothesis space capital H, probability of D given H multiplied by probability of H divided by probability of D. Now, if we observe this expression, the term in the denominator is probability of D. We can drop this term because it is a constant which is independent of h, and hence we can rewrite the expression for h map as it is equal to arg max h belongs to capital H, probability of D given H into probability of H. Now, in some cases, we assume that every hypothesis in the hypothesis space capital H is equally likely or is equally probable. Then, probability of Hi is equal to probability of Hj for all Hi and Hj in the hypothesis space capital H. Here we can further simplify our expression for H map, and we can write a new expression HML is equal to arg max for all hypotheses those belong to the capital H, that is the hypothesis space, P of D given H. Here we are using only one term, probability of D given H, to find the most probable hypothesis. So this term, probability of D given H, is often called as the likelihood of the data D given H, and any hypothesis that maximizes this probability of D given H is called a maximum likelihood hypothesis, HML. To illustrate Bayes' theorem and to better understand the theorem and how it can be applied to solve practical problems, let us consider one example that deals with a medical diagnosis problem. So we have a medical diagnosis problem with two alternative hypotheses. The patient has a particular form of cancer, or the patient does not have the cancer. The data is available from a particular laboratory test with two possible outcomes, positive and negative. There are some facts provided given that over the entire population of people, only 0.008 have the disease. Further, the lab test is only an imperfect indicator of disease. The test returns a correct positive result in only 98% of the cases in which the disease is actually present. It gives correct negative result in only 97% of the cases in which the disease is not present. Now, new patient is observed for whom lab test returns a positive result. So, should we diagnose the patient as having cancer or not? So now let us try to solve this problem. So let us list out whatever has been given. So probability of having cancer is given as 0.008. So probability that there is no cancer is equal to 1 minus 0.008, that is equal to 0.992. Next, it is given that if the report is positive, then only 98% people actually have the cancer. So probability of the test being positive given that cancer is present is given as 0.98. So obviously the probability of negative given cancer is equal to 0.02. Similarly, it is mentioned in the problem statement that if the report is negative, then 97% people do not have cancer. So probability of the test being negative given that no cancer is present is 0.97. So obviously the probability positive given no cancer is 1 minus 0.97, that is equal to 0.03. With this data available with us, a new patient is observed for whom lab test returns a positive result. So whether we should diagnose the patient as having cancer or not, that is what we would like to find. Now let us try to find out the probabilities for both the hypotheses. Hypothesis 1, that patient has cancer. Hypothesis 2, patient does not have the cancer. So probability that patient has a cancer given the data, that is the test is positive, is equal to probability of positive given cancer multiplied by probability of cancer divided by probability of positive, that is equal to 0.98 into 0.008 divided by probability of positive, that is equal to 0.0078 divided by probability of positive. Similarly, we can find out the probability for other hypothesis given data, that is probability having no cancer given positive is equal to probability of positive given no cancer into probability of no cancer divided by probability of positive, which is equal to 0.0298 divided by probability of positive. As mentioned earlier, probability of data, that is probability of positive, can be omitted as it is independent of hypothesis, and hence we may compare the probabilities computed for these two hypotheses. Probability for hypothesis cancer is 0.0078 and probability for hypothesis no cancer is 0.0298. So here we can observe that the probability for the hypothesis no cancer is maximum among these two, and hence H-map is equal to no cancer. So this means that we may say that even though the patient is observed and found the lab test as positive, the patient do not have cancer. And now here is a list of few basic probability formulas. So you are advised to go through these important formulae. So that's all for this session. In the next video, we are going to discuss about Bayes concept learning, learning a real valued function, Bayes optimal classifier, and Gibbs classifier. Thank you.